Okay, hi everybody. Welcome back to the section 6.3 video series. And in this video, we're going to be focusing on the indicial equation. Okay, and what this indicial equation helps us do is kind of verify what those R roots will be, what those R values will be. Okay, so it might be helpful to know ahead of time what these R values might be when we're doing these problems, we're able to find what the R values will be like within the solution process, but how are we sure those are correct? Okay, well, the indicial equation is a good verifying tool to see that we're on the right track. And if your R values are correct, then that means that your recurrence relation and your general terms are also on the right track as well. So, something to do beforehand. So, a good check before you start the problem, solving the differential equation with, the power series, a sub n x to the n plus r. So you want to do it before you start the problem so that you can, verify your work, but it's up to you. But here's exactly how we do it. So, say you want to be in standard form. Okay, so, get into standard form. All right, so you want to be like y double prime plus p of x, y prime plus q of x, y equals 0. Okay, so similar to when you are verifying regular or irregular singular points, you're going to have a little p of x, a little q of x, you're going to have x, x squared. So, little p of x is x times capital P of x, and little q of x is x squared times capital Q of x. You know, x meaning like x minus 0, x squared meaning like x minus 0 squared, because we're centered about the regular singular point x equals 0 here. So, it's the same thing, but that relates to the regular, irregular, singular point check. So there's a couple of values we want to obtain. We want to obtain an A and a B. Okay, so A naught is defined as this little p evaluated at 0. Well, we know little p is x times capital P, so it would be like x times capital P of x, and whatever that is, evaluated at 0. So, little p of x evaluated at x equals 0. So whatever you get for little p of x, you just plug in 0 and you get the answer for A naught. And for B naught, it would be q evaluated at 0, little q. So it's like saying, x squared times capital Q of x evaluated at 0. So, little q of x evaluated at x equals 0. So this very important indicial equation, it's essentially going to be r times r minus 1 plus a naught r plus b naught equals 0. Okay, so that's our indicial equation, and this allows us to solve for r. Okay, it becomes a quadratic equation or some type of equation that sets us up to find the roots for r. Sometimes r is 0, sometimes it's, an actual number, but this is what we work with. So, like I was saying, you sometimes want to check it before you start solving the differential equation, so that while you're in the process of solving the differential equation with your power series, You verify that you got the right roots, and so that like you're on the right track and there's no mistakes or anything. So let's go ahead and try with examples. So we solved example two previously without using this initial equation. Same differential equation from example two. 3xy double prime plus y prime minus y equals 0. And, let's use the initial equation to verify the roots. So we know what the roots are. We did the problem already. Let's like see how this works out. So we want to get into standard form. Okay, so we're going to divide by 3x and 3x. So what we would get is y double prime plus 1 over 3x y prime minus 1 over 3x y equals 0. Okay, and 1 over 3x is my p of x. Negative 1 over 3x is my q of x. Okay, so they are the same thing between a positive and negative difference, but yeah, that's what we're working with. So let's just write it down just for the sake of it. Okay, so we need to get a little p of x, little q of x. We need to get a naught, b naught, and set up our equation. So little p of x is x times p of x, which is x times 1 over 3x. The x's cancel out, and so what I'm left with is just 1 over 3. Okay, and then little q of x is x squared times q of x. That's x squared times negative 1 over 3x. The x cancels out, a copy of the x squared cancels out, so what I'm left with is negative x over 3. Okay, so let's go ahead and get a naught now. A naught is little p evaluated at 0, so that's 1/3 evaluated at x equals 0. Well, there's nowhere to plug in x equals 0, so a naught is just going to be 1/3. Okay, so that's a naught. And then let's look at q or b naught. So that would be uh, negative, or it's q naught, or excuse me, it's q evaluated at 0, which means it's negative x over 3 evaluated at x equals 0. So that means I'm plugging in 0 for x. I get negative 0 over 3, which is just 0. All right, and that's b naught. So the initial equation is going to be r minus 1, excuse me, r times r minus 1 plus a naught r plus b naught equals 0. So let's plug in a and b naught. So this would be r times r minus 1 plus a naught, which is 1/3, times r plus 0 equals 0. And so this simplifies down into distributing the r. We get r squared minus r plus 1/3 r equals 0. Combine the negative 1 and the 1/3 r. So r squared minus 2/3 r equals 0. And we can just solve for r now. So let's factor out an r with r minus 2/3 inside. So that means r equals 0 and r equals 2/3. Okay, and what do we notice? These are the same values for R as in example 2. Okay, so the initial equation checks out. All right, so yeah, a lot of extra work outside of it, but the good thing about it is that like it's a good check. All right, it's a good check to see you're on the right path and you have the right roots, because if you don't have the right roots, the solution's wrong. So maybe you want to do it before, maybe you want to do it like at the point where you're getting the roots. It's up to you, but it's a good check. Okay, so that's it for the initial equation. We'll use this in an example to, double check. All right, but that's it for this intro, and then I'll see you guys in the next video. All right, take care.